Let's look at how to solve a nonlinear inequality in one variable. We want to find where x cubed minus 10x squared plus 24x is less than 0. So this is a cubic function. And what I'm going to do, so we can get an idea of where this should go, I'm going to graph it. And so if we have technology, if we have a calculator, this is pretty straightforward. We can just graph it, and we'll get a sense of where that's less than 0 and greater than 0. So let me just bring the graph up here. Okay, so there it is. What we see is that when x is less than 0, y is less than, so let me make sure we say, hey, we're plotting y equals this. So when x is less than 0, the output, that cubic, the y value, is less than 0. And then there's another region over here between 4 and 6. And so we can just get the answer there. We can say that it's the solution set is minus infinity to 0 and together with 4 to 6. Notice this is not a less than or equal to, and so it's just going to be strict. It's going to be round parentheses here. Okay. So how would we get this by hand is the point. And especially if when you read off the graph, if these weren't integers, how would we know exactly what to say? So, but it's nice to know what kind of answer we're going to get. This is a cubic. It's not surprising that it's got these two different regions because it can turn around twice. Not shocking, it's got these two different regions where the output is negative. Okay, so this is the inequality. The most important thing is do not treat this like a linear inequality, like 3x plus 5 greater than 0. We would manipulate it. We'd move things over, isolate the x. Don't try to isolate x. Inequalities, if they're not just linear, are just more complicated. What the principle really becomes, first look at the equation. So I'm going to take this, I'm going to turn it into the equation equals 0. We know what to do with that. And let me point out, given that we know what this really looks like, that's going to find the zeros. It's going to find the places where the function has the ability to change sign. We know that a 0 of a polynomial, it doesn't always change sign. We're going to have to be careful about that. But at least we'll find the places where it could change from positive to negative and vice versa. And that's the key. So we're going to look at the equation instead. So this is a very general principle. For anything but the simplest inequalities, you actually try to really deeply understand the equation first. And that's going to give you the boundaries of the regions that you're interested in that are going to be defined by the inequality. Okay, now I did pick this that it factors. X factors out. If you can't factor this, you're gonna have trouble. It's gonna be harder. Okay, but that does factor. Okay, so solutions to the equation are x equals 0, 4, and 6. Okay, which, surprise, surprise, that's what we saw with the picture. That's those crossing 0, 4, and 6. Okay, theory, that's what we know how to do, as long as we can factor that guy. So what does this do? It gives intervals, because I know it can only switch at most at those zeros. And if I weren't looking at the graph, we couldn't even be sure that it does switch at those zeros. We know that the possible intervals are, I could try to do that correctly, minus infinity to 0, and then we've got 0 to 4, and 4 to 6, and 6 to infinity. And it's going to have the same sign on all of that interval. It's going to have the same sign on all that interval, on all that, on all that. It can't switch in the middle of the interval because it can't just decide to switch sign without crossing the axis. And so now we just need to test. There's a couple ways to do the last step here, but the most straightforward way to do it, or most low-tech way to do it, is pick this tiny bit of creativity here. Pick simple x values, or pick a simple x value, in each interval, and just test whether it's positive or negative. Pretty straightforward. So for example, if I plug in x equals -1, plug it into the original function here. And so this comes down to just simply evaluating the function 4 times in this case. What's that going to be? It's going to be -1, -10, -24. That's definitely less than 0. I don't even need to know the exact number. Okay, so that tells us that this is one of the intervals where it's going to be either positive or negative consistently, and I now know it's negative simply because I just plugged in a single value, and there was nothing special about -1 except it was the simplest number, just make the arithmetic easier. How about x equals +1? I don't know why I keep doing that. That's going to be to test 0 to 4. Okay, that's pretty easy to plug in as well. We get 1 minus 10 plus 24. That is greater than 0. Okay, and that's confirming what we saw with the graph. Okay, and then just 2 more. So now we are going to go to the next interval. That's between 4 and 6. Obviously, the simplest point in there is x equals 5. Okay, so that's a little more complicated, but not too hard. 5 cubed minus 10 times 5 squared plus 24 times 5. That's not super hard, but I'll let the computer do it. Okay, that is -5, so that's less than 0. And again, that's not super surprising because we know what the picture was going to look like, but this is going to be new information if we don't have the graph. And then x equals 7, super similar. We're just going to plug in 7. So the last stage is really quite straightforward. Once you have the zeros, you stake out your intervals, you pick out some test points in each one of those intervals. Hey, surprise, surprise, it's 21. It's greater than 0. So that's where we found out that the intervals, remember that the inequality we were interested in was where it's negative, and we confirm what we got on with the computer graph, that it's these intervals on the line. So switch to the equality, utterly the most important thing. Really understand the equality. Think of that as the boundary of the regions of inequality, and then test any of the different regions to see which ones have the inequality that you want.